Today we want to start off by looking at some important triangles that we need to know. Important might not be the right word, but it's the word that I'm going to use. We're going to get some angles that we have to remember. We have to remember the sine, cosine, and tangent of 30, 45, and 60-degree angles. We're going to use these to expand into other quadrants. Right now, we've been dealing with acute angles exclusively, because we've been putting everything in right triangles. And so we've been dealing with all these acute angles. But we're going to want to expand, and so we're going to want to have a baseline of some common angles that show up a lot. And so we're going to use 30, 45, and 60 because they come from some easy to remember, come along with some easy to remember ratios. All right. So in an isosceles right triangle, isosceles refers to the fact that two sides of the triangle are equal. And since two of the sides in the triangle are equal, that means the angles opposite those sides must also be equal. Since one of the angles is a 90-degree angle, that means the other two angles must be 45 degrees. We can imagine that we take this isosceles right triangle and cut it out of just a square where all four sides are the same. So I'm going to say that this is a square with a side length of 1. So if the two sides are 1, they have to be the same because it's an isosceles triangle. We can use the Pythagorean theorem to calculate the hypotenuse. So I'll have the square root of 1 squared plus 1 squared, and that'll be equal to the square root of 2. So now we have opposite, adjacent, and hypotenuse for 45-degree angles. So here are some values that we're going to have to remember. The sine of 45 is opposite over hypotenuse. So 1 divided by the square root of 2. The cosine of 45 is adjacent over hypotenuse. So that's 1 over the square root of 2. The tangent of 45 will be opposite over adjacent. And that will be 1 over 1. So the tangent of 45 is 1. In the age of calculators, writing the 1 over the square root of 2 as just 1 over the square root of 2 is perfectly acceptable. But we should also recognize the rationalized form of 1 over the square root of 2. So we used to say things like 1 over the square root of 2 is not simplified. An expression isn't simplified if there is a radical in the denominator. So we have to rationalize our denominator. So 1 over the square root of 2, if I multiply on top and bottom by the square root of 2, I can rewrite this as the square root of 2 divided by 2. So the sine of 45 is the square root of 2 divided by 2. The way that we'll pronounce this is to say root 2 over 2. That's how the cool kids say it. Well, that's how most of the mathematicians say it. I don't know if the mathematicians are the cool kids. They are in my book. So we would pronounce this root 2 over 2. Also, because we're Americans and we tend to mumble things, we'll say things like √2/2. So it'll be kind of like one word. Very German that way, just cram it all together into one big word. So we'll probably say √2/2. One over the square root of 2 is the same as the square root of 2/2. 1 over the square root of 2 is 0.7071. And the square root of, the square root of 2 divided by 2 is 0.7071. So they're the same. So we think of this isosceles right triangle as cutting a right triangle out of a square by cutting it across the diagonal. We can do a similar thing for the 30-60-90 triangle. The 30-60-90 triangle is half of an equilateral triangle. So if we draw an equilateral triangle, equilateral means all the laterals are equal, that is, all the sides are equal. If all the sides are equal, since angles opposite equal sides are equal, all the angles are equal as well. So equilateral means equiangular. Since the sum of the angles in a triangle is 180 degrees, each angle must be 60 degrees. So what we're going to do to make a 30-60-90 triangle is to take our equilateral triangle and cut it in half. Since I cut the triangle in half, I'll cut that angle at the top in half. So a 60-degree angle becomes a 30-degree angle. And that'll make a right triangle with a 60-degree angle down here and a 30-degree angle at the top. The way we want to set this up, since we're cutting one of the sides in half, when we cut that angle in half, I want to make each side equal to 2. So that makes the hypotenuse equal to 2. The side that we cut in half equal to 1. So the side opposite the 30-degree angle is equal to 1. And the hypotenuse is equal to 2. So we can use the Pythagorean theorem to find out what the third side is. Find out what the height of the triangle is. So we'll take the square root of 2 squared minus 1 squared. We'll get the square root of 3. We now have opposite, adjacent, and hypotenuse, so we can calculate sine, cosine, and tangent of 30 degrees and 60 degrees. So let's write them down. The sine of 30 so here's the 30-degree angle. Opposite to 30 is 1, and the hypotenuse is 2. So sine of 30 is 1/2. The cosine of 30 is adjacent over hypotenuse, so that's going to be the square root of 3 divided by 2. The tangent of 30 is opposite over adjacent, which is 1 over the square root of 3. We will often see this in its rationalized form. So instead of 1 over the square root of 3, we'll have square root of 3 over 3. And we will probably mash that together in a mumble, root 3 over 3. Let's also look at the sine, cosine, and tangent of 60 degrees. So the sine of 60 now the 60 degree has a root 3 opposite, so we'll have root 3 over 2. The cosine of 60 adjacent to the 60 degree is a 1, so the cosine of 60 is 1 over 2. And the tangent of 60, still opposite over adjacent, so that's going to be root 3 over 1. So we'll just write that as root 3. These are 9 values that we just have to know now. You don't have to memorize these values, but you do have to remember them. When I say memorize, I mean sit down and just like go back and forth and do whatever it is you do to memorize things. I just want you to remember them. That means I want you to work with them so much, you just remember what they are. I don't want you to know that 7 times 8 is 56 because when you were a kid, you sat down and memorized your times table. I just want you to have multiplied 7 times 8 so much, you just remember that it's 56 now. Think about learning the words to not your favorite song, but any song. You don't really sit down and memorize the words, like sit there and repeating it back and then rewinding and repeating it back. You've just heard the song so much, you remember what the words are. I just want you to remember these values. To that end, we should try to organize them a little bit better than they're presented here, because notice that there's a lot of similarities. Notice that the sine of 30 is a half, and that the cosine of 60 is a half. The sine of 45 is root 2 over 2, and the cosine of 45 is root 2 over 2. This should make sense because if we take the sine of an angle, that will be the same as the cosine of the complement to that angle. Since 45 is the complement of 45, that's why the sine and the cosine of 45 are both the same. Cosine of 30 is root 3 over 2, and sine of 60 is root 3 over 2. So we just want to put together a bunch of things that we can remember. So we can notice this complement thing. That's maybe something that will help us remember these values. For the sines and the cosines, notice that we're using just 3 different values. 1 over 2, root 2 over 2, and root 3 over 2. So the values that we have for sine, cosine, and cosine are root 1 over 2, root 2 over 2, and root 3 over 2. That's handy. There's a short list of things that we need to know. One thing that might help us is to recognize what these values are approximately. We saw that root 2 over 2 was approximately equal to 0.7071. That could prove useful. Root 3 over 2, let's see, what's that one? The square root of 3 divided by 2 is 0.8660. One half is just 0.5, nothing fancy there. Let's see, we've also got this square root of 3 running around. So what is the square root of 3? 1.732. So let's make sure we recognize that. 1.732. And if we take the square root of 3 and divide it by 3, that's 0.5774. Now we've got a quick calculator way to check if we remember which one is which. Because if we can't remember if sine of 30 is a half or cosine of 30 is a half, we can just grab our calculator and say, hey, what's the cosine of 30? Is that a 1/2 or a root 3 over 2? We'll see it's 0.8660. Say, oh yeah, it's the one that's root 3 over 2. Would be helpful in remembering these values. All right. Right now, things are in a really weird order because I have the middle one over here on the left. I have the small one here in the middle and the big one here on the right. So let's maybe try reorganizing. So I'm going to put these in order. I'm going to write the sine of 30. And I'm going to definitely remember that sine of 30 is a half. This is literally the one that I based all this remembering on. I say for sure I'm going to remember sine of 30 is a half. Not even because I remember this triangle. I just remember sine of 30 is a half, like 7 times 8 is 50 something. And then sine of 45 is root 2 over 2, and then sine of 60 is root 3 over 2. Sine of 30 is a half. So sine of 30, sine of 45, sine of 60 is root 1 over 2, root 2 over 2, root 3 over 2, or just count. Sine counts up is the way that it works in my mind. I don't know what's going to work in your mind to help you remember these values. I'm just giving you samples of what happened to work in my mind. Cosine counts down. Cosine of 30 is root 3 over 2. Reinforced, oops, I'm going to spell cosine correctly. Reinforced by the complementary angle thing. Sine of 30 will be the same as the cosine of 60. Cosine of 30 will be the same as the sine of 60. Cosine in my mind goes cosine 30, cosine 45, cosine 60. It counts down in my mind. Root 3 over 2, root 2 over 2, 1 over 2. Then we want to throw tangent into the mix. And I'll put them in tangent of 30, tangent of 45, and tangent of 60. Looks like tangent counts up because tangent of 30 is root 3 over 3. 0.5774. Tangent of 45 is 1. Tangent of 60 is the big one at square root of 3, which is 1.732. This pattern is eventually going to continue on, because we're going to go past 30, 45, and 60, and we're going to drop all the way down to 0 and go all the way up to 90. So we're going to also include, later on, I guess technically I'm including it now, that the sine of 90 is equal to 1. And if we go backwards, we're going to find out that the sine of 0 is equal to 0. We're also going to recognize that I didn't plan this well, because I got to cram this one into this left margin, and I've still got all this space on the right one. But now that you can see that sine of 0 is 0, sine of 30 is a half, sine of 45 is root 2 over 2, sine of 60 is root 3 over 2, and sine of 90 is all the way up at 1, you can probably guess what's going to happen with cosine. What would you guess the cosine of 0 is? Cosine of 0 is equal to 1. Cosine of 30 is root 3 over 2. Cosine of 45 is root 2 over 2. Cosine of 60 is a half. And so the cosine of 90, anyone want to guess what that is? 0 is correct. So we can see sine going up from 0 and sine going from 0 to 1, and cosine going down from 1 to 0. Tangents is a little bit different, because tangent's got the 1 right here. Tangent's not restricted by 0 and 1. But we can use our calculator to find out that tangent of 0 is 0. But on the other end, tangent of 90 is a little bit strange. Tangent of 90 is undefined. But it's undefined in a particular way. Tangent of 90 is going off towards 0. This is not how we would write things, or sorry, going off towards infinity. This is not how we use infinity. We wouldn't want to say the tangent of 90 equals infinity, because nothing equals infinity. That's not how we use infinity. Equals works with numbers. Infinity is not a number. Equal sees infinity come and say, get out of here. I'm not working with you. But we could say, as theta approaches 90, the tangent of theta approaches infinity, as long as we're approaching 90 from angles smaller than 90. This is the organization that makes sense in my mind, especially when I put these end caps on it. I don't know what organization is going to work best to help you remember all these values. The important thing is that you just make an attempt to organize them in such a way that you think you will remember. I kind of think of it like dieting. Like the reason that most diets work when you first start doing them is that when you first start doing the diet, you're actually really paying attention to everything that you eat. And the reason they stop working is not necessarily because the diet is bad, but because you start to get into habits. And then once you're in doing habits with your food, you go back to your old habits, which is what got you to where you were in the first place. So it's hard to say what's going to work. Any questions on remembering these values? Let's talk about why we want to remember these values. We're going to use this to help put angles. We're going to use this to help find sine, cosine, and tangent of angles that are less than 0 and more than 90. So let's talk about angles in standard position. I'm going to use the title of this section, Angles in the Cartesian Plane. So the Cartesian plane is just x, y coordinates that we're familiar with. So let's draw some x and y coordinates. So if you recall, we talked about angles having an initial side and a terminal side. An angle in standard position has its vertex at the origin and its initial side on the positive x-axis. So standard position the vertex is at the origin. And the initial side is on the positive x-axis. And counterclockwise is the positive direction for angles. So if I put a terminal side here, that's theta with a positive measure. So that's the standard position of an angle. The vertex is at the origin, the initial side is on the positive x-axis, and counterclockwise is the positive direction for theta, for angles. What this means is that the positive x-axis will be where we find theta equals 0. So here is where theta is equal to 0 degrees. And we're counting counterclockwise is positive. So up here in the positive y-axis is where theta is equal to 90 degrees. Continuing past 90, the negative x-axis is where we'll have theta is 180 degrees. Continuing around to the negative y-axis, that's where we'll find theta equals 270 degrees. And continuing all the way back to the start, when we're back at the positive x-axis, that is not only a 0 degree angle, that's also a 360 degree angle. And now we find something really weird about this circular number line. Even though the numbers keep going, the locations will be familiar. Because 0 degrees and 360 degrees is referring to the same place on the coordinate plane. Both angles refer to the positive x-axis. So if we kept going, 90 degrees is also 450 degrees. 180 degrees is also 540 degrees. 270 is also 270 plus 360. And 360 degrees is not only also 0, but also 720 degrees. That's why in a jump, if you go or make 2 circles, that's a 720. If we go backwards, going backwards, if I go clockwise, that means 270 degrees can also be known as negative 90 degrees. 180 degrees is also known as negative 180 degrees. 90 degrees can also be negative 270 degrees. So all these angles will have an infinite number of aliases. The other thing that we notice that we know about the Cartesian plane is that the Cartesian plane divides the two-dimensional space into 4 quadrants. So these 2 axes divide space into 4 quadrants. So we're going to divide things into 4 quadrants. And we're going to count them starting in where theta is between 0 and 90 degrees. So this first quadrant is going to be called Q1. And we use Roman numerals to let everybody know that we're serious. And then we count in the same positive direction. So Q1 is between 0 and 90. The second quadrant is between 90 and 180. That's Q2. Between 180 and 270 is third quadrant, which we abbreviate Q3. And then between 270 and 360 is the fourth quadrant, which is QIV. 4. I don't know how the Roman Empire was so successful with this terrible number system. But there it is. We count the 4 quadrants, quadrant 1, 2, 3, and 4, starting with the upper right and going counterclockwise, because that's our positive direction. So we're going to take these angles and we're going to put them in rectangular in the Cartesian plane. We got to know what standard position is. So we can all agree to draw them the same way. We got to talk about the 4 quadrants, which we abbreviate Q1, Q2, Q3, and Q4. The next piece we need to put in is reference angles. So if we have an angle theta, that could be any measure it wants, positive, negative, it could come from anywhere. The initial side is definitely the positive x-axis, but it could be positive or negative, and the terminal side can be anywhere. So we need to talk about reference angles. So for any angle, we need to be able to talk about its reference angle. For an angle theta, the reference angle goes from the terminal side to the nearest x-axis. So the way I describe the reference angle is to say go from the terminal side we're going to call it theta with a subscript of r for reference. Theta r, the reference angle, will be measured from the terminal side to the nearest x-axis. So when we talk about the reference angle for theta, we're going to measure from the terminal side to the nearest x-axis. So let's draw a set of axes. So if I have a theta in the first quadrant, the reference angle goes from the terminal side to the nearest x-axis. So I want to go from the terminal side to the nearest x-axis. This is the angle theta r. If I have a theta in the second quadrant, so this is where the terminal side of theta is. It could be because we measured theta from the positive x-axis or counterclockwise here, or maybe it went backwards clockwise 4 or 5 times before it terminated here. Whatever angle ends here in the second quadrant, the reference angle goes from the terminal side to the nearest x-axis. So we drop it down here. That's where we'll draw theta r. Go from the terminal side to the nearest x-axis. If I have an angle in the third quadrant, however we drew the angle theta, positive or negative, going around as many times, going around the circle completely as many times as we want. If theta terminates in the third quadrant, the reference angle goes from the terminal side of theta here in the third quadrant to the nearest part of the x-axis. So here is where we would draw the reference angle. Finally, if we have theta in the fourth quadrant, We go from measure the reference angle from the terminal side to the nearest x-axis. So that'll be the positive x-axis in the fourth quadrant. That's where we would draw theta r. We care about reference angles because we'll note what we want to notice is the reference angle will always be positive and acute. Reference angles are always between 0 and 90. Theta r is always between 0 and 90 degrees. The reason that this is useful is that there are an infinite number of angles that terminate here on this particular terminal side in quadrant 2. There's an infinite number of angles that we can draw that end here. I can go from the positive x-axis directly there in the positive direction. I can go around once and then continue on to terminate here in the second quadrant. I can go around twice and then terminate 3 times, 1 billion times, 100 billion times, and terminate here. I can even go negative, same thing. I can go negative and terminate in the second quadrant there. I can go full circle negative and then keep going and terminate there. But the reference angle for all those angles that terminate at this location is going to be between 0 and 90. And now we're starting to put together why I care so much about the values of sine, cosine, and tangent for these common angles between 0 and 90. We really need to know what's going on for angles between 0 and 90. And the reference angles are going to help us deal with all these other angles. I'm going to need to justify that this is a good idea and what else we have to do besides this, or you can just take my word for it, which you shouldn't do. I mean, you should require that I convince you. You know what I mean? Don't just take my word for it. You got to question everything. The reason that you're going to more school is so that you will be more equipped to question everything. Especially the things that you believe. And when I say question everything, don't just look, don't do the thing where people think what people think research is, where you just look for stuff that supports your position. You got to be scientists about this. You got to go out there and try to prove yourself wrong. You got to start thinking, what will it take to change my belief? And then go out and look for that. And if your beliefs won't stand up to this kind of scrutiny, then you really got to start wondering why you believe them. You know what I mean? All right. So here's how we find a reference angle, because now we're dealing with angles that are in the Cartesian plane. We're putting angles on an XY axis. The things that we need to know are what standard position is, what the quadrants are, and how to find reference angles. How's everybody okay? Now, this only seems like it's a lot to remember because it's a lot to remember And you have to remember all of it, all the time, in perfect detail. So it is a lot to remember. It's going to be easy for some of you, and it's going to be difficult for others. That's just the nature of things. You know what I mean? So, and the amount of time it takes you to absorb and synthesize all this stuff and remember it when you need it is variable for everybody. That's the tricky part. You're all going to be picking this up at different rates. Some of you have got it already. Some of you are still in the math class where I just say something once and you will remember it forever. And I don't know why that is. There's no magic formula for determining who that is or what it is about the information that makes you remember it forever. Some of you pick things up fast. And some of you are going to struggle very hard for this, just to remember that sine of 30 is a half. For whatever reason, that fact is going to find it difficult. You're going to find it difficult to lodge that fact into your memory to the point where you can recall it when you need it. But this is just the nature of human learning. The most important characteristic is that you persist in your effort to do so. When you find yourself saying something, telling yourself things like, well, maybe I just don't get this. That is the part of your brain that says, I find this unpleasant, go do something fun. That's the part of your brain that's saying, go play Xbox, go warm up the PS4 or PS5, I don't know. I think PS5s are like wealth in the United States. There's like 5 or 6 people that have them, and they have more than they know what to do with. So they're just trying to sell them to people that don't have any money. Brilliant strategy. I'm going to sell this to people that don't have enough money for it. I'm going to take a $500 item and try to sell it for $2,000 to people that don't have $2,000 to spend on it. Then I'm going to wonder why I have so many PS5s in my garage. I actually personally don't. I have one PS4 and it was given to me. I thought I had kicked the habit of consoles. I'm like, oh, phew, my PS3 finally broke down. Haven't played it for years. And all of a sudden, a friend of mine's like, oh, I just got a PS5. I've got this old PS4. I'm like, oh, no. And it's like, oh, here, Leech, you take it. I'm like, oh, you son of a bitch. How did you do this to me? Anyway, just when I thought I was out. What are we talking about? Oh, yes. There's a lot of stuff that you want to just start to remember. So your project for this weekend is to start remembering these values. Start remembering sine of 30 is a half. Sine of 45 is root 2 over 2. Sine of 60 is root 3 over 2. Also throw in sine of 0 is 0 and sine of 90 is 1. Then know your cosines. Cosine of 0 is 1. Cosine of 30 is root 3 over 2. Cosine of 45 is root 2 over 2. That's where sine and cosine meet. Cosine of 60 is down to a half, and cosine of 90 is 0. So cosine and sine are going in kind of different directions. Tangent is a little bit different. Tangent of 0 is 0. Tangent of 30 is root 3 over 3. Tangent of 45 is 1. Tangent of 60 is root 3. And then tangent of 90 is undefined because it's going to infinity. Then take all those angles, draw them in the first quadrant on a Cartesian plane, and identify their reference angles. And then draw each of those reference angles in the other 3 quadrants. And figure out what those angles are going to be. What is a 30-degree reference angle in the second quadrant? What is a 30-degree reference angle in the third quadrant? What's a 30-degree reference angle in the fourth quadrant? Any questions? Then all you have to do is that over and over again until you're incapable of forgetting it. That sounds like a lot of work, but I think that's only because it's a lot of work. All right, that's your project for this weekend. Learn those values, learn how the reference angles work, start the homework from chapter 2. And there is a new quiz on solving right triangles, quiz 3. All right, that's going to do it for this week. If I don't see you tomorrow during office hours, I'll see y'all on Tuesday. Everybody have a good weekend, and thanks for playing.